Welcome to The Explainer. Today we're diving into something truly epic. We're going to map out the history, the staggering future, and just the sheer raw power of stellar catastrophes. We're talking about supernova, literally the most energetic processes in nature. And we're going to track exactly how humanity's understanding of these cosmic explosions has completely shape-shifted over time. You know, it's a contrast of just mind-boggling proportions when you think about it. The absolute vastness of space against the intensely personal reality of our own bodies. So how did explosive celestial omens from 2 millennia ago become the ultimate key to understanding the literal building blocks of you? How do we get from staring up at these terrifying lights in the night sky to suddenly realizing that those very same explosions are directly responsible for the calcium in our bones and the iron in our blood? Section 1. Mysterious portents to modern labs, tracing 2 millennia of stargazing. So, when we look back at the historical sweep of human curiosity around these massive stellar events, it really is a remarkable story of persistent digging. Ancient skywatchers actually called these unpredictable lights guest stars. They would just suddenly appear, sometimes shining so bright they cast shadows in the middle of the day. They'd overstay their welcome for a few months and then, poof, just vanish. Imagine the sheer panic of early civilizations looking at these as celestial portents, thinking they might spell the end of an empire or ruin their harvest. It's kind of funny to contrast that absolute dread with modern astrophysics teams today who are literally hunting for these explosions so they can point every single available sensor at them the second they ignite. And this history spans nearly 2 millennia of super careful observation. It all starts way back in 1805 CE. That's when Chinese astronomers meticulously documented a mysterious guest star that just hung around in the sky for 8 months. Today, we actually know that exact event as SN 185, and astronomers are still studying the expanding remnant of that explosion right now. Fast forward through the 20th century, and major breakthroughs like watching supernova 1987A happen helped our models of stellar evolution mature incredibly fast. And that brings us to today. Right now, international research teams are analyzing deep-field infrared data beaming back from the James Webb Space Telescope. They're piercing right through the dense dust of supernova remnants to map out the specific distribution of heavy elements left behind. And every single new supernova we've observed over those centuries has helped transform those once mysterious omens into comprehensively understood astrophysical laboratories. They have absolutely fundamentally reshaped our models of stellar evolution. They give us precise data on the mass loss rates of progenitor stars right before they go critical. Plus, they've provided the standard candles we absolutely need to map out cosmic structure and actually measure the accelerating expansion of the universe. But crucially, they've let us decode the complex chain of nucleosynthesis. We can now map out exactly how the extreme pressures and temperatures of a core collapse forge the heaviest elements in the periodic table. Section 2. Next-generation cosmic observatories, unprecedented rates of discovery. All right, so we are currently standing on a huge technological frontier, looking at upcoming facilities like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope. The Rubin Observatory, running its legacy survey of space and time, is gearing up to scan the entire visible southern sky every few nights using a massive 3,200 megapixel camera. It's going to catch transient events the literal moment they flare up. Meanwhile, the Roman Space Telescope will use a field of view 100 times greater than Hubble to capture just vast swaths of deep-field infrared data. These aren't just minor incremental upgrades. We're talking about paradigm-shifting tools here that are going to fundamentally revolutionize our statistical understanding of exactly how stars die. And honestly, the sheer scale of what's coming is hard to even overstate. We are talking about millions. These new facilities are expected to detect potentially millions of stellar explosions over their operational lifetimes. We're making this massive leap from logging just a handful of historical guest stars, or even a few thousand discoveries a year like we do now, to an absolute deluge of cosmic data. This unprecedented data set is going to allow researchers to spot incredibly rare subtypes of supernova that we previously missed entirely, letting us fine-tune our astrophysical models with a level of precision that was literally impossible just a decade ago. Section 3. The Multi-Messenger Frontier, adding new observational dimensions. So picture this. During the chaotic core collapse of a massive dying star, the implosion is so wildly asymmetric and violent that it actually produces ripples in the very fabric of space and time. Space-time ripples! These are gravitational waves. Now, while we've already detected these waves from merging black holes and neutron stars, a core collapse supernova happening in our own galactic neighborhood would generate a completely unique gravitational wave signature. If we can capture that signature directly, it would let us peer straight into the dense, churning heart of the explosion, an environment that's completely, totally hidden from traditional light-based telescopes. And that is exactly the essence of the multi-messenger approach. By combining complementary perspectives, we get a fully unified, multi-dimensional picture of these events. We don't just rely on electromagnetic detection anymore, like visible or infrared light. We're also hunting for these elusive little particles called neutrinos. Because neutrinos interact so weakly with matter, they actually escape the collapsing star hours before the explosive shockwave even reaches the star's surface to produce visible light. So they act as this ultimate early warning system. They allow observatories all around the world to point their instruments at the exact right patch of sky just before the visible light arrives, while at the exact same time measuring the gravitational wave detections those space-time ripples produce. It is, without a doubt, the absolute cutting edge of supernova research. Section 4. Our Place in the Cosmos, the Stardust Connection. Okay, now for the big zoom in. We're taking this massive scale of international scientific collaboration, millions of exploding stars, ripples in space-time, and we're connecting it directly back to you, to our own physical existence. This centuries-long scientific journey reveals nature's most energetic, fundamental cosmic processes. But listen, this isn't abstract physics. These are the exact processes that created the elements of our bodies. The calcium in your bones, the iron in your blood. Exactly like we mentioned at the start, they were literally forged in the unimaginable heat of a collapsing star. Through galactic chemical evolution, they seed the interstellar medium with the heavy elements we need to form rocky planets like ours. They provide the foundational ingredients that sustain life right here on Earth. So, through this incredibly persistent human curiosity and technological innovation, we've come to the profound realization that we are, quite literally, made from the catastrophic, chaotic results of stellar death. And as we keep refining our understanding of these extreme astrophysical events, we simultaneously deepen our appreciation for our own place in the cosmic narrative. It's a story, quote, one written in the brilliant, fleeting light of dying stars. So, I want to leave you with a final thought to ponder tonight. When you step outside and look up at the night sky, do you see distant omens? Or do you see the ancient laboratories that forged the very elements you are made of? Keep that perspective with you. Thank you so much for joining me for this explainer. Keep your curiosity alive, and as always, keep looking up.